A billion particles of antimatter meet a billion particles of matter, and almost everything vanishes into light. But somewhere in that ancient cosmic fire, one extra particle remains. From that tiny imbalance come galaxies, stars, planets, and every atom in the human body. The universe exists because perfect symmetry fails by the smallest imaginable margin. This is the antimatter mystery, a question hidden inside every piece of ordinary matter, asking why anything survives at all. If this quiet journey into the deepest laws of nature feels worth sharing, leave a like, subscribe for more long-form science, and send this video to someone who enjoys cosmic mysteries before sleep. Thank you for spending part of the day or night here. What time is it where this video is playing, and where in the world is it being watched? Leave a comment below. Now, let the last traces of the early universe lead into the mystery of why existence escapes annihilation. The universe begins in a state where almost everything familiar is impossible. There are no stars, no planets, no atoms, and no quiet darkness between galaxies. Space is filled with heat and radiation, and the particles that will one day form matter appear only as brief possibilities within that energy. In this early environment, nature seems to follow a simple balance. Whenever enough energy becomes a particle of matter, an equal amount of antimatter should appear beside it. The two forms match one another almost perfectly. They carry the same mass. They respond to the same basic rules, yet their electrical charges and certain other properties are reversed, as though each particle arrives with a mirror companion. An electron has a positron, a proton has an antiproton, a neutron has an antineutron. For every known building block of matter, the laws of physics allow an opposing version. This symmetry is elegant, but it makes the existence of anything solid difficult to explain. Matter and antimatter cannot peacefully occupy the same place. When a particle meets its antiparticle, both disappear in an event called annihilation. Their mass becomes energy, often in the form of high-energy light or other particles. The process occurs in laboratories, radioactive decay, and violent cosmic environments. Antimatter is real, and its encounter with matter is final. If the early universe creates equal amounts of both, then nearly every particle should eventually find its opposite. Protons should meet antiprotons, electrons should meet positrons. One by one, the ingredients of atoms should erase one another, leaving behind a universe flooded with radiation but almost empty of matter. In such a universe, gravity has little material to gather. No broad clouds of hydrogen form, no stars ignite, no heavy elements are forged in stellar cores, no rocky worlds cool beneath distant suns. The structures that now fill the sky never begin. Yet the real universe does not resemble that barren outcome. It contains galaxies woven into immense filaments, clusters bound by gravity, stars burning through long ages, and planets assembled from the remains of older suns. Ordinary matter survives everywhere telescopes can see. It survives in interstellar gas, stellar interiors, dust grains, ocean water, living cells, and planetary stone. Every atom becomes evidence that the expected annihilation is incomplete. The mystery is not that antimatter exists. The mystery is that matter remains. The difference appears extraordinarily small at the beginning and overwhelmingly important afterward. Calculations based on the abundance of matter and radiation suggest that for roughly every billion particles of antimatter in the early universe, there may have been about 1,000,000,001 particles of matter. The first billion pairs destroy one another. The single extra particle has no partner left to meet. That tiny residue survives as the universe expands and cools. Over immense stretches of time, those survivors become everything that now has mass and form. The balance is almost perfect, but not completely. Existence depends on the failure of symmetry by the narrowest imaginable margin. The surviving matter is the trace left after nearly total destruction. The stars are built from leftovers. Galaxies are monuments to a minute imbalance. Every world is assembled from particles that escape because there are slightly more of them than there are antiparticles. This picture gives the universe a strange character. The visible cosmos appears vast, but in a deeper accounting it is the residue of an event that removes nearly everything. The abundance of photons in space carries part of that history. The universe contains far more particles of light than particles of ordinary matter, consistent with a past in which enormous numbers of matter and antimatter pairs annihilate, while a small excess remains. The afterglow of the early universe therefore hints at a vanished population, a balanced sea of particles and antiparticles from which almost nothing survives. The problem becomes sharper because the known laws of particle physics do not obviously begin with a preference for matter. The equations generally treat particles and antiparticles as closely related partners. Matter is not marked as the natural winner. Antimatter is not assigned a lesser status. Both can be created from energy, carry momentum, and form bound systems. Antiprotons and positrons can combine into antihydrogen, a mirror version of the simplest atom. In principle, antimatter could build antiatoms, antimolecules, anti-stars, and anti-galaxies. An antimatter world would not look ghostly from within. Its chemistry could follow familiar patterns, and its stars could shine by the same broad physical processes. The distinction becomes dramatic when the two domains touch. Contact turns structure back into radiation. This raises an early possibility. Perhaps matter does not truly dominate the entire universe. Perhaps some distant regions contain antimatter, separated from ordinary matter by enormous voids. A galaxy made of antistars could emit light much like a galaxy made of stars. Light carries no electric charge, so a telescope cannot simply identify the sign of the matter that produces it. From a great distance, an anti-galaxy might resemble an ordinary one. The idea offers a simple escape from the puzzle. Matter may gather in one region, antimatter in another, and annihilation may be avoided because the two rarely meet. Yet this solution creates its own difficulties. Boundaries between large matter and antimatter regions should become active sites of destruction. Gas drifting across them should annihilate and produce distinctive high-energy radiation. Cosmic rays might also carry antinuclei from distant antimatter structures into detectors near Earth. Searches continue for such signs. But the universe so far appears overwhelmingly dominated by matter across the observable region. Small amounts of antimatter are constantly produced in energetic events, but there is no clear evidence for vast nearby domains made primarily from it. The missing antimatter does not seem to be waiting just beyond the next galaxy. Another possibility reaches further back. Perhaps the early universe does not create perfect equality. Perhaps a process occurs during the first moments of cosmic history that gives matter the slightest advantage. The required advantage is tiny, but producing even that small difference demands a change in the known story. Some interaction must distinguish matter from antimatter. Some process must alter particle numbers without preserving exact balance. The early universe must also provide conditions in which the new imbalance is not immediately erased. These requirements turn the mystery into a search for hidden physics, somewhere between the first hot state and the later formation of atoms. Nature follows a path that favours matter by a fraction so small that it almost disappears in the mathematics, yet large enough to determine the future of the cosmos. Experiments show that matter and antimatter are not perfect reflections in every respect. Certain unstable particles decay in slightly different ways from their antiparticles. This difference, known as a violation of charge and parity symmetry, proves that nature can favour one direction over its mirror, but the known effects appear too weak to create the full cosmic imbalance. They reveal that the door is open without showing what passes through it. Neutrinos may hold part of the answer. Unknown particles may act in the extreme energies of the early universe. Phase changes in fundamental fields may briefly place nature out of balance. Processes linked to forces that merge only at enormous energies may transform particles in ways no present accelerator can directly reproduce. Each idea attempts to explain the same quiet fact matter receives one extra chance to survive. The mystery reaches beyond particle physics because it touches every later chapter of cosmic history. Without the imbalance, gravity has no lasting material to shape. Chemistry has no stable atoms to combine. Time may continue, space may expand, and radiation may cool, but the universe never develops familiar structure. The existence of matter is therefore not a minor detail added after the beginning. It is one of the conditions that allow the beginning to lead anywhere. The question of antimatter becomes a question about why the universe has a history filled with objects rather than only a fading glow. No complete answer yet commands agreement. The surviving matter may arise from subtle behavior already hidden within known particles, or from a deeper layer of physics that appears only under conditions long vanished from the cosmos. The imbalance may be connected to neutrinos, unknown heavy particles, ancient transitions in the Higgs field, or principles not yet recognized. The evidence begins with what remains and points backward into an era that cannot be observed directly. The universe stands as the result of a nearly perfect cancellation that somehow fails. Its galaxies, stars, planets, and living systems emerge from that failure. In the darkness between the stars, matter seems abundant and secure, yet its presence records a narrow escape from non-existence. The first mystery is not hidden at the edge of space or inside an exotic object. It is present in every ordinary atom. Each one carries the same unresolved message the universe should have vanished into light, but it did not. Long before antimatter becomes a cosmic mystery, it first appears as an unwanted answer inside an equation. The setting is the late 1920s, when physics is being rebuilt almost from its foundations. Quantum mechanics has revealed that particles do not behave like tiny solid objects moving along clear paths. Relativity has shown that space and time are joined, that energy and mass are related, and that no material influence outruns light. Each theory is powerful, but bringing them together is difficult. The electron stands at the center of the problem. It is one of the simplest known particles, yet its behavior refuses to fit neatly inside the available mathematics. At low speeds. Quantum mechanics describes it with remarkable success. Near the speed of light, however, relativity can no longer be ignored. A complete equation must respect both worlds at once. Paul Dirac takes up this task with an unusual faith in mathematical structure. He searches not for a mechanical picture that can be visualized easily, but for a form that is internally consistent, compact, and beautiful. The result is an equation that describes the electron with a precision and elegance unlike anything that comes before it. It also produces something deeply unsettling. The equation does not yield only the familiar electron. It contains a second set of solutions, equally valid in the mathematics, associated with energies that appear to have the wrong sign. In ordinary reasoning, a particle cannot simply possess less than no energy. The result seems absurd, perhaps a flaw in the equation or a meaningless branch that should be ignored. Yet the unwanted solutions cannot be removed without damaging the structure that makes the equation work. The mathematics insist that they belong. Dirac first tries to interpret them without introducing a new kind of particle. At the time, physics is cautious about multiplying the contents of nature. A new particle is not proposed lightly, especially one that no experiment has seen and no familiar theory requires. The proton is already known, and Dirac briefly wonders whether the strange positive counterpart might somehow be related to it. But the proton is far heavier than the electron, and the comparison fails. The second solution continues to remain where the equations place it, neither disappearing nor accepting an ordinary identity. This resistance matters. The problem is not a decorative feature of the mathematics. It lies at the heart of the attempt to make quantum mechanics compatible with relativity. The equation succeeds because it treats energy and momentum in a new way and includes the electron's intrinsic spin naturally. The same structure that explains known behavior also opens the door to an unknown world. To preserve the success, the mystery must be faced. Dirac begins to consider a radical possibility. Perhaps the second solution is not a mathematical mistake. Perhaps it describes a real particle with the same mass as the electron, but with opposite electric charge. Such a particle would be a mirror of the electron, similar in nearly every measurable way, yet reversed in one crucial sign. The proposal is difficult not because it is vague, but because it is so precise. It predicts an object that has not been inserted by hand. It emerges from the equations as the cost of consistency. The new particle is later called the positron, a name that marks its positive electric charge. In the modern view, it is the electron's antiparticle. The idea expands quickly beyond one case. If the electron has an antiparticle, then other particles may as well. The theory points toward a general pairing in nature. Every particle can possess a corresponding antiparticle with the same mass and spin but opposite values for certain charges. Matter is no longer the only form allowed by the laws. A parallel set of building blocks becomes possible, not as fantasy but as a direct consequence of the mathematical framework. The step is enormous. It doubles the conceptual inventory of the particle world. Yet at the moment of proposal, there is no guarantee that nature has chosen to realize the second half. Equations can contain possibilities that the universe never uses. The decisive question is whether the mirror particle can be found. The answer arrives from cosmic rays, high-energy particles that strike Earth's atmosphere and produce showers of secondary fragments. In the early 1930s, Carl Anderson studies these events using a cloud chamber, a device filled with vapor in which charged particles leave visible trails. A magnetic field bends the paths. The direction of curvature reveals the sign of the electric charge, while the amount of bending helps indicate the particle's momentum and mass. In one photograph, a track appears that behaves like an electron in mass but curves as though its charge is positive. The path is not easily explained as an ordinary electron moving in the opposite direction. Careful analysis shows that the strange track matches the particle Dirac's equation predicts. The positron has been found. A mathematical discomfort becomes a physical object. The discovery changes the meaning of the second solution. It is no longer an embarrassment to be hidden inside formalism. It becomes evidence that the equations have reached beyond what experiment already knows. This moment also changes the relationship between mathematics and nature. The equation does not merely organize known observations. It reveals a hidden symmetry that reality later confirms. The prediction is not a guess based on a faint experimental hint. It comes from insisting that two great theories must coexist without contradiction. From that demand, an unseen particle enters physics. The achievement is profound, but it also deepens the mystery introduced by antimatter. Once the positron is real, matter no longer appears unique. The electron is only one member of a pair. The familiar negative charge is not more fundamental than the positive charge of its counterpart. Both belong to the same structure. Nature seems capable of creating either form, and under suitable conditions it creates them together. Energy can transform into an electron and a positron, provided conservation laws are respected. The reverse process also occurs. When the pair meets, both vanish into radiation. Creation and annihilation become two directions of the same physical relationship. The mirror is not separate from the ordinary world, it is woven into it. Antimatter appears in radioactive processes, particle collisions, and cosmic interactions. It is produced wherever enough energy is concentrated in the right way. The positron's discovery therefore does more than add one particle. It shows that empty space, energy, and matter are linked through rules that allow opposites to emerge and disappear. The older picture of permanent particles moving through a passive void begins to dissolve. Particles become excitations that can be created, transformed, and destroyed, while deeper symmetries govern which processes are allowed. In the language that later develops, particles and antiparticles belong to quantum fields that fill space. An electron is not a tiny bead that exists independently of everything else. It is a particular excitation of an electron field. The positron is another excitation of that same field, carrying opposite charge. This view makes antimatter less exotic and more unavoidable. It is part of the basic grammar of relativistic quantum theory. The same framework eventually describes quarks and antiquarks, neutrinos and antineutrinos, protons and antiprotons, though composite particles such as protons are built from more fundamental constituents. Antimatter is not a separate substance added beside matter. It is the reflected possibility contained within the laws that describe matter itself. Yet the symmetry remains incomplete in the visible universe. The theory that predicts the positron gives no simple reason for electrons to fill galaxies, while positrons appear mainly in brief or isolated events. The mathematical pairing is clear. The cosmic outcome is not. Dirac's equation therefore opens two doors at once. One leads to a triumphant prediction confirmed by experiment. The other leads toward the unresolved question of why one side of the mirror dominates the universe. The equation succeeds so completely that its unanswered implication cannot be dismissed. If every particle has an antiparticle, and if energy can create them together, then the early universe should naturally contain both. The discovery that validates the theory also sharpens the threat of annihilation. The same symmetry that reveals a hidden world makes the survival of ordinary matter harder to understand. Dirac begins with an effort to describe a single electron moving near the speed of light. He ends by exposing a second architecture of nature, equal in mass, opposite in charge, and inseparable from the first. The unwanted answer does not vanish. It becomes real, and once it does, the universe itself becomes more difficult to explain. The prediction of antimatter becomes convincing only when nature leaves a track. Mathematics can open a possibility, but a visible trace in a detector gives that possibility weight, direction, and consequence. In the early 1930s, cosmic rays provide the first path from Dirac's equation into the physical world. These energetic visitors strike Earth from space and collide with atoms high in the atmosphere, producing showers of secondary particles that race downward through air, rock, and instruments. Most vanish quickly. Some leave brief records. In a cloud chamber, vapor condenses along the path of a charged particle, drawing a thin line where something invisible has passed. A magnetic field bends that line. The direction of the bend reveals whether the particle carries positive or negative charge, while the curvature gives clues about its momentum. In one of Carl Anderson's photographs, a track appears that behaves like an electron in almost every way, yet curves as though its charge is positive. It is too light to be a proton, and too precisely matched to be dismissed as noise. The discovery does not arrive as a dramatic flash. It appears as a narrow arc in a chamber, a silent curve whose meaning emerges only through careful measurement. Yet that curve changes physics. The electron is no longer alone. Nature possesses a mirror particle with the same mass and the opposite charge. The mathematical symmetry is real. From that point onward, antimatter can no longer be treated as a strange possibility hiding at the edge of theory. It is part of the particle world, present wherever energy and the laws of conservation allow it to appear. The positron also reveals an important pattern. Antimatter is often born in pairs with matter. A sufficiently energetic photon can transform near an atomic nucleus into an electron and a positron. The original light carries no electric charge, so the total charge of the new pair must remain balanced. One particle is negative, the other positive. Their paths curve in opposite directions inside a magnetic field, opening like two branches from the same point. Energy becomes mass, but it does so without losing the symmetries that govern the interaction. The process confirms that antimatter is not a separate foreign substance entering the universe from elsewhere. It can emerge directly from energy beside ordinary matter. The reverse process follows with equal clarity. When an electron and positron meet, their identities disappear and their mass returns to energy. Commonly as photons, creation and annihilation form a matched pair of possibilities. The same laws that bring opposites into existence allow them to erase one another. After the positron, the search expands toward heavier antiparticles. This is more difficult because mass carries an energy cost. An electron is light, and energetic cosmic events produce positrons relatively easily. A proton is nearly 2,000 times heavier than an electron, so creating an antiproton requires far more energy. The process must also conserve charge and other quantum properties. An antiproton cannot simply appear by itself. Matter and antimatter must emerge in a larger balanced reaction, usually amid many other particles that complicate the evidence. In the mid-1950s, accelerator experiments at Berkeley finally produce and identify the antiproton. Protons are driven to high energy and smashed into a target. The collision concentrates enough motion into a small region for new particle pairs to form. Among the debris, a negatively charged particle appears with the proton's mass. It is the antiproton, built from antiquarks rather than quarks. Its discovery extends the mirror beyond the electron. Antimatter can possess internal structure. It can form the counterpart of a composite particle, not merely the opposite of a single elementary charge. The antineutron follows soon after, carrying no net electric charge but differing from the neutron in the arrangement of its internal quantum properties. These discoveries confirm that the reflected world has depth. Quarks have antiquarks, protons have antiprotons, neutrons have antineutrons. The known architecture of matter can, at least in principle, be rebuilt with every component reversed. The idea of antiatoms moves from speculation toward experiment. An antihydrogen atom requires an antiproton to serve as the nucleus, and a positron to occupy the surrounding quantum state. It is the simplest neutral atom of antimatter, matching hydrogen in mass and basic structure. Producing it is conceptually straightforward and practically severe. Antiprotons must first be created in violent collisions. They emerge at high speed and must be slowed. Positrons must be gathered from separate sources. The two populations must be brought together without touching ordinary matter. Then, after the neutral antiatom forms, it must somehow be kept from drifting into the walls of the apparatus, where it will annihilate instantly. Each stage requires fields, vacuum, cooling, patience, and extraordinary control. The first antihydrogen atoms are produced in the late 20th century, but they move too quickly to study for long. Later experiments at CERN create colder antihydrogen and eventually trap individual antiatoms using carefully shaped magnetic fields. Neutral antimatter does not respond to electric fields in the simple way a charged antiproton does, but its magnetic properties allow it to be confined inside a magnetic minimum. The trap is delicate. The antiatoms carry little energy, yet even a small disturbance can send them into surrounding matter. When the trap is released or an atom escapes, annihilation products reveal where it strikes. For brief periods, the mirror atom is held away from the material world that would destroy it. This achievement is less about quantity than control. The amount of antimatter involved is almost unimaginably small. Accelerators can produce millions of antiprotons in a run, but that number represents only a tiny fraction of a grain of matter. Even after long periods of operation, the total mass remains microscopic beyond ordinary experience. Antimatter is not difficult to create in the sense that nature forbids it. It is difficult to create efficiently, slow down, assemble, store, and study. Most of the energy used in production becomes other particles and heat. Only a minute share ends as trapped antimatter. The laboratory therefore resembles a workshop devoted to preserving a few sparks from an enormous fire. Yet the scarcity of laboratory antimatter should not be mistaken for evidence that antimatter is unnatural. Small quantities appear continuously in the universe. Cosmic ray collisions produce positrons and antiprotons. Certain radioactive isotopes emit positrons. Violent environments near pulsars, black holes, and stellar explosions generate particle and antiparticle pairs. The difference between these local appearances and the cosmic mystery is scale and survival. Antimatter appears in small amounts wherever high-energy processes produce it, but it does not seem to accumulate around ordinary matter. A positron moving through material soon encounters an electron. An antiproton entering gas soon meets a proton or nucleus. Annihilation prevents large mixed populations from lasting. For antimatter to form stable planets or stars, it would need to gather in regions largely separated from matter. Laboratory production shows that antiatoms are possible. It does not show where the vast primordial antimatter population has gone. Each successful experiment sharpens that absence. The positron proves that the mirror exists. The antiproton proves that the mirror contains heavier structure. Antihydrogen proves that antimatter can form atoms. Nothing in these achievements suggests that ordinary matter is uniquely suited to complexity. If enough antimatter were isolated, it could in principle build larger antiatoms, antimolecules, clouds, and stars. The chemistry would arise from the same electromagnetic rules, with every charge reversed. Light from an anti-star would look much like light from a star because photons are their own antiparticles and carry no electric charge. A distant antimatter world might therefore appear deceptively familiar. The laboratory confirms the ingredients of such a world, while the sky withholds clear evidence that one exists nearby. Antimatter becomes real in stages first, a curved line in vapour, then a heavy antiparticle among collision debris, then an antiatom held briefly in a magnetic trap. Each stage removes another reason to dismiss the reflected universe. What begins as a second mathematical solution becomes a family of particles, then a form of atomic matter. The mirror is no longer theoretical. It can be created, measured, cooled, and confined. Yet this success makes the original puzzle more severe. If nature permits antimatter so readily in its laws, and if energy naturally creates matter and antimatter together, then the early universe should have contained both in abundance. The detectors prove that the missing half is physically possible. They do not explain why the cosmos is built almost entirely from the other half. Every positron track and every trapped antihydrogen atom therefore carries two meanings. It confirms a triumph of theory, and it points toward a disappearance on the larger scale. The mirror world is real, but somewhere between the first moments of the universe and the formation of the first stars, almost all of it seems to have vanished. Creating antimatter is not the same as keeping it. In high-energy collisions, Particles and antiparticles appear as brief products of concentrated motion, but most of them vanish almost as soon as they are made. The difficulty begins with the ordinary matter that surrounds every laboratory: walls, air, wires, dust, and instruments are all built from particles that annihilate their antimatter partners on contact. An antiproton cannot rest on a table. A positron cannot be poured into a glass container. Even the slightest touch becomes a final event. The challenge is therefore not simply to produce the mirror form of matter, but to build a region in which it can exist without meeting the material world. Modern antimatter research depends on creating such regions with vacuum, electric fields, magnetic fields, and extremely careful control. The production process starts with ordinary particles accelerated to enormous energies at facilities such as CERN. Protons are taken from hydrogen and pushed forward by electromagnetic fields. They gain speed through a sequence of machines until they approach the speed of light. The protons then strike a dense target. Their kinetic energy becomes a crowded spray of new particles. Among the many fragments are antiprotons, each born beside other particles in a reaction that preserves the balances required by physics. The target does not produce a clean beam of antimatter. It produces confusion, pions, protons, fragments, and radiation emerge together, while the antiprotons occupy only a small part of the debris. Magnets must separate particles according to charge and momentum, selecting a narrow stream from the collision. Even after this sorting, the antiprotons are moving far too quickly for precision experiments. They are created in violence, but they must be studied in stillness. Slowing them down requires a machine that works like an accelerator in reverse. CERN's antiproton decelerator receives the fast particles and reduces their energy in stages. Electric fields remove momentum while magnetic systems keep the beam focused. The process is delicate because a beam of charged particles naturally spreads. As the antiprotons lose speed, small differences in their motion become more important. Cooling techniques reduce that disorder, bringing the particles into a tighter range of energies and directions. The word cooling does not necessarily mean placing them against something cold. Contact with material would destroy them. Instead, the beam is made more orderly through controlled electromagnetic interactions. The antiprotons emerge much slower than before, yet still moving rapidly by ordinary standards. A further system must capture them. Charged antimatter can be confined because electric and magnetic fields act across empty space. A trap creates a landscape that the particles cannot easily leave. Electric potentials act like invisible hills and valleys for charge. Magnetic fields bend the paths of moving particles, forcing them into spirals rather than straight lines. In a penning trap, these effects are combined so that antiprotons circle within a vacuum, suspended away from the walls. They do not sit motionless in the center. They orbit, bounce, and drift inside the field, tracing patterns that remain unseen until detectors record their behavior. The trap contains no physical surface for the antimatter to touch. It holds the particles at a distance. Maintaining the vacuum is essential. Even a small amount of residual gas contains atoms that can collide with trapped antiprotons. Pumps remove as much gas as possible, producing pressures far lower than those found in ordinary environments. The apparatus is also kept cold because thermal motion can disturb the trap and increase the chance of escape. Every layer of protection serves the same purpose, preventing a tiny population of particles from encountering a single atom in the wrong place. In this setting, storage becomes an exercise in avoiding almost everything. The laboratory does not build a stronger box. It removes the box from the antimatter's path and replaces it with fields. Positrons require their own collection system. They can come from radioactive sources that naturally emit them during certain decays. These positrons begin with a spread of energies and must also be slowed, cooled, and gathered. When enough antiprotons and positrons are confined, researchers can attempt to combine them into antihydrogen. The antiproton forms the nucleus, while the positron occupies a surrounding quantum state. In principle, the arrangement mirrors ordinary hydrogen. In practice, the particles do not join merely because they are placed near one another. Their energies must be low enough for capture. If they move too quickly, they pass without binding. If they collide with the apparatus, they disappear. Experiments therefore overlap clouds of antiprotons and positrons under carefully controlled conditions, waiting for a fraction of them to form neutral antiatoms. Neutrality solves one problem and creates another. An antiproton is electrically charged, so electric fields can confine it strongly. Antihydrogen has no net charge. Once formed, it no longer responds to electric potentials in the same direct way. It can drift out of the charged particle trap and strike the wall. To hold it, researchers rely on its magnetic character. The positron and antiproton within antihydrogen give the atom a tiny magnetic response. Special arrangements of magnets create a region where certain antihydrogen atoms have lower energy near the center than near the edges. This magnetic minimum acts as a shallow bowl. Only the coldest antiatoms remain inside it. Faster ones climb out and annihilate. Producing antihydrogen is therefore only the beginning. The real achievement is producing it gently enough to remain trapped. When the magnetic field is later changed, the antiatoms escape and strike surrounding matter. Their annihilation releases particles that detectors trace back to points around the trap. From these signals, researchers infer how many atoms were held and where they were lost. The antiatoms are detected by their disappearance. Every successful storage event ends in a burst that confirms the object had survived until the trap was opened. The quantities involved are almost beyond ordinary scale. A facility may create millions or billions of antiprotons over time, yet their combined mass remains minuscule. A visible speck of dust contains vastly more ordinary particles than even the most productive antimatter experiments store. The energy cost is equally severe. Accelerators consume large amounts of power, but only a tiny fraction becomes trapped antimatter. Most energy is lost in the production process, carried away by unwanted particles, radiation, heat, and beam inefficiency. Antimatter is not scarce because the laws resist its creation. It is scarce because the path from input energy to preserved antiparticles is extraordinarily wasteful. Popular stories sometimes imagine grams of antimatter stored as compact fuel or explosives. Present technology remains nowhere near that scale. The problem is not merely expense. A macroscopic quantity would require impossible levels of production, cooling, confinement, reliability, and protection from failure. The traps used in research are designed for minute populations under controlled conditions. They reveal physical laws, not practical reservoirs of energy. Their value lies in precision. A single trapped antiproton can be measured again and again. A small cloud of antihydrogen can be exposed to laser light. Tiny samples can test whether antimatter obeys the same spectral rules as matter or falls under gravity in the same way. The laboratory turns scarcity into an advantage by isolating simple systems so carefully that small deviations might become visible. The act of holding antimatter is itself a proof of symmetry. Antihydrogen remains stable when isolated. It does not instantly decay merely because it is antimatter. Its danger comes from contact, not from internal fragility. In empty space, an antiatom can persist. This suggests that large antimatter structures would be possible if they formed in regions free from ordinary matter. An antistar would not need a magnetic trap. Its own antimatter would provide the environment around it, just as matter surrounds an ordinary star. The laboratory difficulty arises because antimatter is being preserved inside a world made almost entirely of its opposite. Each experiment is a tiny artificial island, separated from the surrounding universe by vacuum and fields. Within that island, the mirror can remain for seconds, minutes, or longer, depending on the system. The achievement seems modest only until the conditions are considered. Nature creates antiparticles freely in high-energy events, but human instruments must catch them while they are racing, cool them without touching them, combine them without losing them, and hold the resulting atoms inside barriers made of nothing solid. The process transforms a violent collision into a quiet measurement. It narrows an enormous storm of particles down to a handful of survivors. Those survivors are among the most carefully protected objects ever made. They exist at the center of elaborate machines, surrounded by matter that would erase them, held in place by invisible forces that never allow direct contact. The mirror world is therefore not stored in a container. It is suspended in absence. Its preservation depends on emptiness, precision, and the continuous shaping of fields. Every trapped anti-atom shows that antimatter can endure, but only while the ordinary universe is kept at a careful distance. Once antimatter can be created and held, a deeper question comes into view. Does the mirror behave exactly like the original, or does nature hide a difference too small to notice without extraordinary care? The visible universe suggests that some difference must exist somewhere, because matter survives while antimatter is scarce. Yet every simple comparison points toward near equality. An antiproton has the same mass as a proton within experimental precision. A positron has the same mass as an electron. Antihydrogen appears to share the basic structure of hydrogen. The two forms respond to electric and magnetic fields in opposite directions where charge demands it. But those reversals do not by themselves explain why matter dominates the cosmos. The search, therefore, moves into finer territory. Instead of asking whether antimatter is broadly different, experiments ask whether its properties depart from matter by a fraction so small that only the most stable instruments can reveal it. When charge, spatial reflection, and the direction of time are considered together, the laws of a local quantum field theory predict that a particle and its antiparticle must possess equal masses and lifetimes while carrying opposite charges. This combined symmetry is known as CPT symmetry. Nature is already known to violate some simpler symmetries, but CPT symmetry stands deeper in the framework. A confirmed violation would force a reconsideration of the basic structure used to describe particles and fields. Antimatter experiments therefore serve two purposes at once. They search for the cause of the cosmic imbalance, and they test whether the foundations of particle theory remain exact. Charged antiparticles provide one route. An antiproton confined in a magnetic trap follows a curved path whose frequency depends on its charge, mass, and the magnetic field. By measuring this motion with extreme precision, researchers can compare the antiproton's charge to mass ratio with that of the proton. Magnetic fields drift, electrical potentials fluctuate, and the apparatus shifts slightly with temperature. Each disturbance can imitate a difference that does not belong to nature. Experimental design therefore becomes an art of cancellation. Measurements are alternated, fields are monitored, and reference particles are used so that imperfections can be separated from genuine asymmetry. The result is a comparison so exact that any ordinary difference has nowhere to hide. So far, the antiproton continues to match the proton to astonishing precision once the opposite sign of charge is taken into account. This agreement does not solve the mystery, but it narrows the range of possible answers. If matter and antimatter differ, the difference is not a simple mismatch in mass or charge at the level already tested. Neutral anti-atoms offer another path. Antihydrogen is especially valuable because ordinary hydrogen is among the most thoroughly understood systems in all of physics. A hydrogen atom contains one proton and one electron. Its energy levels form a precise pattern determined by quantum mechanics. When light of the right frequency reaches the atom, the electron can move from one energy state to another. The atom absorbs the light only when the energy matches the gap between those states. Later, the electron can fall back and release light with a characteristic frequency. These spectral lines act like a fingerprint. If antihydrogen is truly the mirror of hydrogen, its positron and antiproton should produce the same pattern. A difference in the spacing of the lines would indicate that antimatter follows a slightly altered rule. Measuring this requires trapped antihydrogen cold, enough to remain inside a magnetic field, while lasers pass through the chamber. Researchers tune the laser across a narrow range. Then watch for evidence that the antiatoms have changed state or escaped the trap. An annihilation at the wall can become the final mark of a successful transition. In this way, light interrogates an atom that cannot be touched. The best comparisons continue to show that antihydrogen and hydrogen agree within the reach of present measurements. Again, the mirror holds. Yet every improvement matters because the early universe may depend on a deviation far smaller than current sensitivity. The search also turns toward magnetism. Protons and antiprotons behave like tiny magnets. Their magnetic moments determine how they respond to external fields. The antiproton's magnetic properties match the protons in magnitude, with the expected reversal associated with charge. The pattern is striking. At each level where a broad difference might have appeared, symmetry survives. Mass, charge, spectral structure, and magnetism all line up with remarkable accuracy. The universe appears matter-dominated, but the particles themselves refuse to reveal an obvious preference. Gravity adds another layer because it connects antimatter to the large-scale structure of space and time. Electric charge reverses between particles and antiparticles. But mass and energy do not. In general relativity, gravity responds to energy and momentum rather than to electric sign. The natural expectation is that antimatter falls downward in Earth's gravitational field just as matter does. But the question must be tested. Antimatter has rarely existed long enough in a slow, neutral state for gravity to act in a measurable way. Charged antiparticles are poor probes because electric and magnetic forces overwhelm gravity by enormous factors. A tiny stray field can move an antiproton far more strongly than Earth's pull. Neutral antihydrogen is better, but only if it is made extremely cold. A fast antiatom crosses an apparatus before gravity has time to bend its path noticeably. The experiment must reduce motion until the faint downward influence can emerge from the noise. One approach releases trapped antihydrogen and records where the atoms annihilate. If gravity pulls downward, more antiatoms should reach lower parts of the chamber in a pattern that can be compared with simulations. Another approach sends a horizontal beam of antihydrogen and measures the slight curvature of its trajectory, like an almost imperceptible arc. These experiments are technically severe because magnetic fields used to hold the atoms can also push them, and the forces being compared differ greatly in strength. Even so, the goal is conceptually simple. Does antimatter fall in the same direction as matter A results showing upward motion would be revolutionary and profoundly difficult for existing physics. It would require a new account of gravity, energy, and perhaps the relationship between particles and fields. The expectation remains that antimatter falls downward, though the exact strength of that fall continues to be tested with increasing precision. The absence of dramatic differences shifts attention towards subtler forms of asymmetry. Matter and antimatter may share equal masses and matching spectra, while still differing in how unstable particles decay. Such differences are already known in systems containing quarks. Certain particles transform into their decay products at rates that are not perfectly mirrored by their antiparticles. This is called CP violation, a breaking of the combined symmetry between charge reversal and spatial reflection. It shows that nature is not completely indifferent to matter and antimatter. Yet the amount of known CP violation in the quark sector appears insufficient to create the cosmic excess. The laboratory therefore faces a strange situation. The large properties match almost perfectly, while the small differences that do exist seem too weak. The answer may lie in a sector not yet measured well enough. Perhaps among neutrinos, or in particles too heavy to be produced directly. It may arise only under the extreme conditions of the early universe, when temperatures and densities allow interactions that no longer occur naturally. Every agreement between hydrogen and antihydrogen limits theories that predict simple differences. Every matching measurement of protons and antiprotons closes another opening. Every gravity experiment tests whether the imbalance could be tied to a hidden repulsion or altered response to space-time. The work proceeds by making the mystery narrower. Nature has asked the same question in many languages: motion in a trap, frequencies of light, magnetic response, free fall, decay patterns. The replies remain almost symmetrical. This near perfection deepens rather than softens the puzzle. The universe is built from matter, but the most direct measurements find no ordinary property that grants matter an obvious advantage. Antimatter behaves as though it belongs to the same laws, carries the same stability, and occupies the same possibilities. The difference that shapes the cosmos is therefore unlikely to be simple. It may be hidden in rare transformations, ancient departures from equilibrium, or interactions that appear only at energies beyond present machines. The mirror remains intact under every careful gaze, yet somewhere in the history of the universe, the reflection fails just enough for one side to endure. The missing antimatter may seem, at first, to offer an easy escape from the cosmic puzzle. Perhaps it is not missing at all. Perhaps it simply lies far away, gathered into regions that never touch the matter around Earth. In that picture, the early universe still begins with equal quantities of matter and antimatter, but expansion separates them before annihilation can erase both. One part of the cosmos becomes filled with ordinary galaxies, while another becomes filled with anti-galaxies. Anti-stars burn within them. Anti-planets orbit in quiet darkness. Their atoms are built from antiprotons, antineutrons, and positrons. But their outward appearance may be almost indistinguishable from the structures made of ordinary matter. An anti-star can shine because the processes that release energy inside it do not depend on the familiar sign of electric charge. An anti-galaxy can gather under gravity, form clouds, produce generations of stars, and send light across space. Photons carry no electric charge, so light arriving from a distant anti-star does not arrive marked as antimatter. To a telescope, a bright point made from antimatter can look much like a bright point made from matter. This makes the idea difficult to dismiss by sight alone. The universe could, in principle, hide its reflected regions behind the neutrality of light. Yet the possibility becomes harder to maintain when the boundaries are considered. Matter and antimatter cannot remain indifferent when they meet. If a matter galaxy and an antimatter galaxy share a surrounding cloud of gas, atoms drifting across the border should encounter antiatoms. Their contact should produce annihilation, releasing energetic particles and gamma rays. A large boundary would not be silent. It would glow with the signs of mutual destruction. Even if the galaxies themselves remain separated, the thin gas between them is not perfectly still. Gravity pulls material through clusters. Stellar winds carry particles into surrounding space. Galaxies collide, merge, and pass through shared reservoirs of gas. Over cosmic time, matter and antimatter domains would leak into one another. The resulting radiation should appear in characteristic patterns across the sky. Searches for such patterns do not reveal clear evidence for nearby anti-galaxies. The absence is not absolute proof, because distance, background radiation, and uncertain astrophysical processes can hide weak signals. But it pushes any large antimatter domain farther away and makes the simple picture of a neatly divided universe increasingly difficult. The problem extends from boundaries to cosmic rays. These high-energy particles travel through the galaxy and sometimes reach detectors near Earth. Most are protons and atomic nuclei. A smaller fraction are electrons, positrons, antiprotons, and other particles created in violent events or in collisions between cosmic rays and interstellar gas. If anti-stars or anti-galaxies exist, they may release heavier antinuclei, just as ordinary stars and explosions release ordinary nuclei. An antihelium nucleus would be especially important. Antiprotons can be produced in collisions between ordinary particles, so their presence does not require a distant antimatter world. Antihelium is far harder to make through secondary collisions in large quantities. A convincing detection of antihelium with the right energy and abundance could point toward an astrophysical source built from antimatter. Instruments carried above Earth search for such rare particles, examining the curvature of their paths in magnetic fields and the patterns of energy they leave behind. The challenge is extreme because ordinary nuclei vastly outnumber possible antinuclei, and a mistaken identification can resemble a discovery. A single unusual event is not enough. The signal must survive careful checks against detector effects, background reactions, and errors in reconstruction. So far, no widely accepted detection establishes the existence of an anti-star or anti-galaxy. The search continues because the reward would be profound. A confirmed heavy anti-nucleus arriving from space would show that antimatter has not vanished everywhere. It would reveal that some region has preserved enough of it to build complex nuclei, and perhaps stars, over immense periods of time. Without such evidence, the observable universe remains overwhelmingly matter-dominated. Small amounts of antimatter appear, but they appear as products of local high-energy processes rather than as fragments of a hidden cosmic civilization of antiatoms. Positrons are created in radioactive decay, pulsar environments, black hole systems, and collisions. Antiprotons are produced when energetic cosmic rays strike interstellar material. These particles do not require primordial antimatter domains. They arise naturally from ordinary matter when enough energy is concentrated. Their presence therefore confirms the laws of particle creation, but does not solve the missing antimatter problem. The distinction is crucial. Antimatter exists throughout the universe in traces, yet trace production is not the same as large-scale survival. A spark of antimatter can appear wherever energy allows a particle and antiparticle pair to form. A galaxy of antimatter requires an ancient population to remain separate from matter since the early universe. The first is common enough to measure. The second remains unseen. Cosmology adds another difficulty. The young universe is not a quiet collection of isolated islands. It is hot, dense, and strongly mixed. Particles collide constantly. Radiation couples to matter. Regions that later become galaxies begin as small variations in a much more uniform background. For matter and antimatter to separate before annihilation, some mechanism must sort them over large distances while the universe is still extremely young. That sorting cannot simply rely on electric charge. because matter and antimatter include both positive and negative constituents. Ordinary matter contains positive protons and negative electrons. Antimatter contains negative antiprotons and positive positrons. A basic electric field does not divide the universe neatly into matter on one side and antimatter on the other. Any separation mechanism must act on deeper properties, and it must do so rapidly enough to prevent widespread annihilation. It must also produce domains large enough that their boundaries do not flood the universe with observable radiation. No simple and accepted process achieves all of this. Inflation, the early period of rapid expansion proposed in modern cosmology, can stretch tiny regions to enormous scales. But it does not automatically create a matter domain here and an antimatter domain elsewhere. A theory must first generate the difference between those regions and then preserve it through expansion, and later, evolution. Some speculative models attempt this, allowing the balance between matter and antimatter to vary across space. In such a model, the observable universe may lie inside one vast matter domain, while antimatter domains exist beyond the distance light has had time to cross. This possibility is difficult to test because anything beyond the observable horizon cannot send information to Earth. It preserves logical room for a larger balanced cosmos, but it does not explain the local asymmetry in a directly measurable way. It moves the missing antimatter beyond reach rather than showing how it survives. The most distant parts of the observable universe also appear to follow the same broad matter-dominated pattern. Galaxies form, gas clouds interact, and the large-scale web develops without obvious annihilation boundaries. The farther telescopes look, the further back in time they see, yet no clear transition appears where ordinary galaxies give way to anti-galaxies. This does not prove that none exist at extreme distances, but it weakens the expectation that matter and antimatter occupy neighbouring cosmic provinces. The sky seems less like a patchwork of opposites, and more like one overwhelmingly matter-filled region. That conclusion turns the mystery back toward the beginning. If antimatter is not hiding in large nearby structures, then the early universe probably does not preserve equal populations in separate places. Instead, something changes the balance before annihilation ends. A slight excess of matter remains everywhere within the region that becomes observable. The missing antimatter is not transported to a distant refuge. It is destroyed, while the unmatched residue survives. This explanation fits the absence of annihilation boundaries and the scarcity of heavy antinuclei, but it demands a process that creates the imbalance. The search for anti-stars and anti-galaxies therefore performs an important role even without a discovery. It tests whether geography can solve what particle physics struggles to explain. Each quiet gamma-ray map, each ordinary cosmic ray spectrum, and each failed search for heavy anti-nuclei makes separation less persuasive. The universe does not appear to hide an equal mirror half nearby. The reflected cosmos remains possible only in remote or carefully arranged forms, beyond the reach of simple observation. Antimatter exists as brief sparks, rare particles, and laboratory atoms, but not as a confirmed realm of stars. The missing half of creation leaves no clear border, no distant glow, and no unambiguous fragment in a detector. Its absence becomes another form of evidence. The sky does not reveal where the antimatter went. It only deepens the suspicion that, in the first moments of cosmic history, it loses a contest decided by almost nothing. The matter that fills the present universe may descend from an excess so small that it almost disappears inside the larger story of annihilation. In the earliest hot stages, particles and antiparticles are created in enormous numbers. Energy moves through a dense, rapidly changing plasma, and collisions constantly turn radiation into pairs of matter and antimatter. A particle appears with its counterpart, preserving the balances required by the laws of physics. At first, this process runs in both directions. Matter and antimatter form from energy, meet again, and return to radiation. Creation and destruction occur so frequently that no lasting structure can emerge. The universe is too hot for atoms, too crowded for stable nuclei, and too energetic for most particles to remain separate for long. In this environment, the difference between a perfectly balanced cosmos and the universe that eventually forms may amount to only one extra particle of matter among roughly 1 billion matched pairs. That single survivor is not important because of its individual mass. It is important because the same tiny advantage repeats across the whole expanding universe. Wherever there are 1 billion antiparticles, there are slightly more particles. The difference is almost nothing compared with the total population, yet annihilation magnifies it. As the universe expands, its temperature falls. The energetic collisions that create heavy particle pairs become less common. Matter and antimatter continue to find each other, but fewer new pairs appear to replace them. The balance begins to empty. Each particle that meets its antiparticle vanishes into radiation. The paired populations fall together, leaving behind only the unmatched excess. The arithmetic is simple and severe. If 1 billion particles of matter face 1 billion particles of antimatter, nothing remains but energy. If 1,000,000,001 particles of matter face 1 billion antiparticles, the annihilation removes the first billion from each side, and one particle remains. The visible universe is built from that remainder. Every galaxy, star, planet, ocean, cloud, and living cell belongs to the side that has one particle left without an opposite partner. This does not mean that a single ancient proton becomes a star. It means that the same fractional excess exists everywhere on a vast scale. The number of survivors is immense because the early population is immense. A tiny fraction of an enormous quantity can still fill the cosmos. The surviving matter later gathers under gravity, but before that happens it passes through long eras of cooling and transformation. Quarks combine into protons and neutrons. Some of those particles form the first light nuclei, much later. Electrons settle around nuclei to create neutral atoms. Gas collects into clouds, clouds collapse into stars, and stars forge heavier elements. None of this later complexity changes the original accounting. The ingredients of structure are the residue left after nearly complete cancellation. The universe looks abundant because the remnant spreads across great distances, but compared with the original sea of particles and antiparticles, it is sparse. The evidence for this history survives in the relationship between matter and radiation. Photons vastly outnumber the particles that make up ordinary matter. Part of that abundance reflects the early universe itself, and part of it is consistent with the enormous release of energy from matter and antimatter annihilation. The present cosmos contains only a small amount of ordinary matter for every large population of photons. This ratio acts like a faint record of the time when almost all massive particles disappear. It suggests that the universe does not preserve most of what it creates. It burns through an early population, allowing opposites to erase each other until only the slight imbalance remains. The term baryon asymmetry describes this excess of matter over antimatter. Baryons are particles such as protons and neutrons, built from quarks, and they provide most of the mass in ordinary atoms. The asymmetry is often described through the difference between the number of baryons and antibaryons. Today, the observable universe contains abundant baryons and almost no primordial antibaryons. The question is not merely why the numbers differ now. Annihilation makes that outcome easy once a difference exists. The deeper question is how the difference first appears. A small excess cannot be added casually to a theory that otherwise creates perfect symmetry. Some process must distinguish matter from antimatter, change the relevant particle numbers, and occur under conditions that prevent later reactions from restoring equality. The magnitude of the excess makes the mystery more delicate, not less. A large imbalance might point toward an obvious force or dramatic separation. A difference of roughly 1 part in a billion suggests a mechanism that is both weak and universal. It must act almost invisibly, yet it must operate across the early cosmos with enough consistency to shape everything that follows. The process may involve rare decays, unstable fields, neutrinos, or physics at energies far beyond present laboratories. Whatever the mechanism, it must leave the universe close to balanced while preventing exact cancellation. That narrow requirement explains why the problem has resisted a simple answer. Nature already shows small differences between matter and antimatter in certain particle decays. These effects prove that the two are not governed by perfect mirror behavior in every process. Yet the known differences in quark systems appear too limited to produce the observed cosmic abundance. They can contribute to a symmetry, but not enough under the simplest calculations. The measured imbalance of the universe therefore points toward additional sources of asymmetry, unfamiliar conditions, or both. The early cosmos may use known laws in a regime where their combined effect becomes stronger, but many physicists suspect that some missing ingredient is required. The one survivor among a billion becomes a clue to new physics. Its smallness gives theories a target. A successful explanation must not produce too much matter, because a larger excess would change the later universe. More surviving baryons would alter the formation of nuclei, the balance of radiation and matter, and the development of cosmic structure. Too little asymmetry would leave too few atoms for galaxies and stars. The observed universe occupies a narrow outcome between near emptiness and a very different cosmic history. Measurements of the cosmic microwave background and the abundance of light elements allow researchers to estimate the amount of ordinary matter that survives from the early universe. These independent records broadly agree, suggesting that the matter excess is a real feature of the primordial cosmos rather than a local accident. The microwave background carries patterns formed when atoms first allow light to travel freely. Those patterns depend on how much ordinary matter is present. The abundance of hydrogen, helium, and other light nuclei depends on the density of baryons during the first stages of cosmic nucleosynthesis. Both lines of evidence point back toward the same small surviving fraction. The residue is measured not by observing annihilation directly, but by reading the structures that the residue later influences. This makes the asymmetry both ancient and present. It belongs to the first moments, yet it remains visible in the amount of gas inside galaxies, the rhythm of acoustic patterns in primordial light, and the chemical composition of the oldest matter. Every observation of ordinary matter is a measurement of survival. The universe does not reveal the vanished pairs individually. Their disappearance is too early and too complete. Instead, it reveals the unmatched remainder, and from that remainder, the original near balance is inferred. The image is quiet but immense. An early ocean of particles and antiparticles thins as space expands. Opposites meet and dissolve into light. The process continues until the great majority are gone. No boundary protects the survivors. No special shelter keeps them apart. They remain only because there are slightly more particles than antiparticles. The last unmatched members of the larger population continue forward while their partners do not exist. From those survivors, gravity eventually builds the visible cosmos. The stars are not made from the dominant substance of the earliest moment. They are made from what annihilation fails to remove. This turns abundance into a form of rarity. Matter surrounds every ordinary experience. Yet on the deepest scale, it may represent only the narrow margin left by a nearly perfect symmetry. The universe exists not because destruction is weak, but because the balance is imperfect. A difference too small to notice in an ordinary sample becomes decisive when the sample is the entire cosmos. One extra particle among a billion is enough, repeated across all space, to leave a universe capable of structure, chemistry, and time recorded in matter. The mystery now contracts into a precise question, not where the antimatter hides, and not whether annihilation occurs, but what causes the first unmatched particle to appear. The answer lies inside a deviation so slight that almost everything vanishes before its importance becomes visible. The tiny excess of matter cannot simply be declared at the beginning and left unexplained. A universe that starts with perfect balance will remain balanced unless some process changes the accounting. In the late 1960s, Andrei Sakharov gives this problem a more exact form. Rather than proposing one complete mechanism, he identifies the conditions that any successful mechanism must satisfy. His insight is not a finished answer but a set of gates. If even one remains closed, matter and antimatter cannot end with different abundances. If all can open together, the early universe gains a path from symmetry to survival. The first condition concerns the number of baryons. Protons and neutrons belong to the baryon family, while antiprotons and antineutrons carry the opposite baryon number. In ordinary low-energy processes, the total baryon number appears to be conserved. A proton does not simply disappear into light, and an antiproton does not spontaneously become a proton. If this conservation were exact under every circumstance, then an early universe beginning with equal baryons and antibaryons could never create an excess. Their numbers might be rearranged, but the difference between them would remain zero. A successful theory must therefore allow reactions in which baryon number changes. Some process must create baryons without creating the same number of antibaryons, destroy antibaryons more efficiently, or begin with another type of imbalance that can later be converted into baryons. The required reactions may be extremely rare today. They may occur only at energies so high that the modern universe almost never reaches them. Their absence in ordinary matter does not mean they are impossible in the first moments, when temperature and density place particles inside a very different regime. The search for proton decay is partly a search for this first opening. If a proton can eventually transform into lighter particles, baryon number is not an absolute law. No proton decay has been confirmed, and measured lifetimes are extraordinarily long. But the possibility remains central to grand unified theories. Other mechanisms avoid direct proton decay at accessible rates while still allowing baryon number to change in the early universe. The first gate, then, demands that the apparent stability of matter is not perfect under all conditions. The second condition concerns symmetry itself. Even if baryon number can change, a process that treats matter and antimatter identically will still produce equal results. For every reaction creating matter, the mirrored reaction will create antimatter at the same rate. The universe may become busier, but it will not become unbalanced. Nature must therefore violate the symmetry between particles and antiparticles. Sakharov expresses this through the breaking of charge conjugation and the combined symmetry of charge and parity. Charge conjugation replaces particles with antiparticles. Parity reflects spatial directions, exchanging left with right. If both symmetries were exact, matter and antimatter reactions would occur as perfect mirrors. Yet experiments show that the weak interaction does not respect these reflections completely. Certain particles decay differently from their antiparticles. The difference is small, but it proves that the second gate can open. Nature does possess processes with a preference. The challenge is magnitude. The The known violations among quarks are real, but appear insufficient, by themselves, to account for the cosmic excess. A successful mechanism may need additional sources of asymmetry, perhaps among neutrinos or heavy particles that no longer exist. It may also need the known effects to operate under early conditions that amplify their influence. The second condition does not say how large the preference must be. It says only that without some preference, balance cannot break. The third condition is less intuitive and just as essential. The universe must depart from thermal equilibrium. In equilibrium, every reaction is balanced by its reverse. Particles transform in one direction and return at matching rates. Any small asymmetry produced by one process is washed away by another. Equilibrium is a state of constant activity without lasting change in the statistical balance. To preserve an excess, the early universe must pass through a period when reactions cannot keep up with changing conditions. Expansion provides one natural way to achieve this. As space grows, temperature falls. A heavy particle may decay while the reverse process, which would recreate it, becomes too slow or energetically difficult. A field may change its state during a phase transition, creating bubbles or boundaries where reactions occur differently. The universe can then leave equilibrium, and an asymmetry produced during that interval may survive after the relevant interaction shut down. This third gate gives cosmic history an active role. Matter does not win only because of the properties of particles. It may win because the universe changes faster than some processes can respond. Timing becomes part of the explanation. The same reaction in a perfectly stable environment might produce no lasting effect, while in an expanding and cooling cosmos, it can leave a permanent residue. The three conditions work together. Baryon number violation allows the accounting to change. Broken matter-antimatter symmetry gives the change a preferred direction. Departure from equilibrium prevents the result from being immediately erased. None is enough alone. Baryon-changing reactions in perfect symmetry create equal matter and antimatter. Asymmetric reactions that conserve baryon number cannot produce a net baryon excess from zero. Both effects inside equilibrium are undone by reverse processes. Only their combination gives the universe a chance to retain one extra particle among a billion. This framework turns the mystery into a testable program. Every proposed origin of matter must show where each condition appears. Grand unified theories often supply heavy particles whose decays violate baryon number and favour matter slightly over antimatter. Electroweak baryogenesis looks to the era when the electromagnetic and weak forces separate and the Higgs field settles into its present state. If that transition is sufficiently strong, and if new sources of symmetry violation exist, expanding boundaries between phases might create a baryon excess. Leptogenesis begins instead with an imbalance among leptons, often involving heavy neutrinos, and later converts part of that imbalance into baryons through processes permitted by the standard model at high temperature. Different mechanisms place the black box in different eras, but all must pass through Sakharov's gates. The conditions also explain why the answer may remain difficult to observe directly. The decisive particles could be far heavier than anything current accelerators can produce. The relevant transition may occur when the universe is only a tiny fraction of a second old. The asymmetry may arise through reactions that leave no surviving particles, only the imbalance they create. Present experiments therefore search for indirect traces. Proton decay would reveal that baryon number is not sacred. New patterns of CP violation would show stronger matter-antimatter differences. Neutrino measurements could expose asymmetries large enough to support leptogenesis. Studies of the Higgs field and searches for new particles test whether the early electroweak transition can behave as required. Each experiment approaches one gate, even when the full passage remains hidden. Sakharov's framework does not guarantee that a mechanism satisfying the conditions will produce the observed universe. The rates, masses, temperatures, and timing must also align. A theory may generate too little asymmetry, too much, or an excess later erased by other reactions. It must survive constraints from particle experiments, cosmology, and the measured abundance of matter. The conditions are necessary, not sufficient. Their power lies in showing why ordinary equilibrium physics cannot solve the problem. Something must violate a familiar conservation rule. Something must distinguish the mirror from the original. Something must happen during a period when the universe cannot restore balance. The origin of matter is therefore tied to a brief failure of reversibility. The early cosmos is not merely hot, it is changing. Its expansion carries reactions out of step, and within that temporary disorder a small preference can become permanent. Once the universe cools further, the gates close. Baryon-violating processes become rare. Heavy particles disappear. Phase transitions end, and the surviving excess is locked into protons and neutrons. Later, physics preserves what earlier physics creates. The stable matter of the present universe may therefore be the fossil of an unstable moment when the usual rules were incomplete in practice. Sakharov's conditions give that moment a shape without revealing its exact contents. They describe the outline of the black box, a place where counting changes, mirrors fail, and equilibrium breaks. Somewhere inside that combination, the billion matched pairs vanish and the one unmatched particle remains. The discovery that nature distinguishes matter from antimatter does not arrive through a difference in mass, charge, or gravity. It appears instead in the slow decay of unstable particles, in patterns so subtle that they require years of measurement and carefully controlled beams. The first decisive evidence emerges in the 1960s from particles called neutral kaons. These particles are built from quarks and antiquarks, and they can transform into one another before decaying. Their behavior is governed by the weak interaction, the same force responsible for certain forms of radioactive decay. Under a perfect mirror symmetry, the decay of a particle and the decay of its antiparticle should match when charge is reversed and space is reflected. Yet the kaons refuse to obey this rule exactly. In 1964, experiments reveal that a small fraction decay, in a way forbidden by the expected combined symmetry of charge and parity. Nature has chosen a slight preference. The mirror is not perfect. This result is profound because it proves that matter and antimatter are not merely separated by opposite signs. Their histories can unfold at slightly different rates. A particle can favour one decay path while its antiparticle favours the reflected path by a tiny amount. The effect is called charge and parity violation. It supplies one of Sakharov's necessary ingredients for creating a cosmic matter excess. Without such a violation, every reaction that produces matter more often would be matched by another producing antimatter at the same rate. The universe could change its particle populations, but it could not choose a winner. The kaon result shows that the laws do contain a preference, however faint. For a moment, the ancient mystery seems to have found its opening. Perhaps the imbalance measured in the laboratory is the same imbalance that saves matter in the early universe, yet the scale of the effect soon becomes the central problem. The observed violation is real, but calculations show that the known pattern among quarks is far too weak to produce the surviving matter. The universe needs roughly one extra baryon among about 1 billion matched matter and antimatter particles. The standard model, using the known quark interactions and known Higgs behavior, appears to generate an excess many orders of magnitude smaller under the simplest early universe conditions. The exact estimate depends on assumptions about temperature, phase transitions, and particle masses, but the conclusion remains stable. The measured asymmetry points in the right conceptual direction while falling far short in strength. It is a key that turns slightly inside the lock without opening the door. The source of this violation lies in the way quarks change type through the weak interaction. Quarks come in several forms, and transitions between them are controlled by a pattern of mixing. This mixing contains a complex phase, a mathematical feature that allows matter and antimatter decay amplitudes to interfere differently. The effect first appears in kaons and is later studied in particles containing bottom quarks. Dedicated experiments produce vast numbers of these short-lived particles and compare their decay patterns with those of their antiparticles. The measurements confirm that the asymmetry is not a flaw in one detector or a peculiarity of one particle. It belongs to the structure of the standard model. Matter and antimatter genuinely behave differently in certain weak decays. The bottom quark systems reveal large and intricate forms of charge and parity violation, while charm particles provide additional tests. Across these experiments, theory and observation agree with remarkable precision. This agreement is a triumph, but it sharpens the cosmic problem. The known mechanism works exactly as expected, and what it predicts is not enough. The missing asymmetry cannot easily be hidden inside ordinary quark behavior, because the relevant parameters are measured closely. The same success that confirms the standard model limits its ability to explain the universe. A theory can fail by disagreeing with experiment, but it can also fail by agreeing too well while leaving a larger fact untouched. The quark sector describes the observed decays, yet the cosmic abundance of matter remains beyond its reach. The weakness comes partly from the structure of the known particle spectrum. The matter-antimatter difference depends on the way multiple generations of quarks mix, and on the separations between their masses. If certain quarks had equal masses, much of the effect could be transformed away and would lose physical meaning. The actual masses are different, so the violation survives, but the combination that matters in the hot early universe is strongly suppressed. In addition, the transition associated with the Higgs field in the standard model does not appear violent enough to drive the universe far from equilibrium in the required way. Instead of a sharp first-order phase transition, the known Higgs mass points toward a smooth crossover. The field changes its state, but not through expanding bubbles with strong boundaries that could efficiently separate reactions and preserve an excess. One of Sakharov's gates opens slightly through quark asymmetry, while another does not open widely enough under the same theory. The full mechanism stalls. This does not make the known violation irrelevant. It demonstrates that nature is capable of breaking the mirror, and it gives physicists a precise language for searching elsewhere. New particles could carry additional phases and create stronger asymmetries. A richer Higgs sector could change the early transition from a smooth crossover into a more abrupt event. Heavy quarks or other unstable particles could decay out of equilibrium and favor matter. Supersymmetric models, grand unified theories, and other extensions introduce new opportunities, though none has yet gained decisive experimental support. Each proposal must respect the measurements already made. New asymmetry cannot simply replace the known pattern. It must hide at energies or in particles that have escaped detection, while leaving the successful low-energy theory largely intact. This constraint makes the search narrow and demanding. The universe appears to require new behavior, yet the laboratory leaves little room for careless additions. The failure of the known effect also encourages attention to neutrinos. Their masses are tiny, their mixing is large, and their relation to antimatter remains partly unknown. If neutrinos and antineutrinos violate charge and parity symmetry strongly, the early universe may generate an imbalance first among leptons rather than baryons. High-temperature processes could then transfer part of that lepton excess into ordinary matter. In that scenario, the quark asymmetry remains real but secondary. It does not create the universe alone. It becomes one example of a wider principle, a visible trace of the kind of symmetry breaking that may be much stronger in a quieter and less understood sector. Experiments therefore compare neutrino and antineutrino oscillations, searching for differences in how they change flavour over distance. The result may reveal a new source of asymmetry, though connecting any measured difference to the exact cosmic abundance will still require a theory of the early universe. The known quark violation also teaches caution. Discovering a difference between matter and antimatter is not the same as explaining existence. A laboratory effect may satisfy one necessary condition while failing in magnitude, timing, or connection to barrier number. The cosmic mechanism must combine several features at once. It must alter the relevant particle accounting, distinguish matter from antimatter, operate away from equilibrium, and leave behind the observed amount without later erasure. No single measurement proves all of this. The path from a decay asymmetry inside a detector to the matter content of galaxies crosses an enormous gap in energy, time, and environment. Theory must bridge that gap, and every step must survive independent tests. The kaon discovery therefore occupies an unusual place in the story. It is both a breakthrough and a warning. It ends the idea that matter and antimatter are perfect mirrors under every interaction. It confirms one of the conditions required for cosmic survival. At the same time, it shows how a genuine clue can remain insufficient. Nature permits a preference, but the known preference is too faint. The universe appears to amplify nothing. It requires a stronger source that has not yet been found. Somewhere beyond the measured quark decays. Another asymmetry may wait in neutrinos, heavy particles, hidden fields, or the dynamics of the early cosmos. The existing violation marks the direction but not the destination. The mirror cracks in the laboratory, yet the fracture is too small to account for the world built on one side of it. Neutrinos enter the antimatter mystery almost without leaving a trace. They carry no electric charge, interact only weakly with ordinary matter, and pass through planets, stars, and living bodies in immense numbers without disturbance. Their quiet behaviour makes them difficult to detect, but it also makes them valuable. A particle that rarely interacts can preserve information from environments that more strongly interacting particles cannot escape. In the early universe, when heat and density erase almost every fragile pattern, neutrinos may carry a hidden imbalance across the changing plasma. Their properties are unusual enough to offer what the quark sector does not. They have tiny masses, they mix strongly, and their relationship to their own antiparticles remains uncertain. These features make them candidates not merely for revealing the origin of matter, but for creating the first difference from which ordinary matter later emerges. Neutrinos come in three known types, usually called electron, muon, and tau flavors. A neutrino created with one flavor does not necessarily keep that identity as it travels. Quantum mechanics allows it to exist as a mixture of states with slightly different masses. Because those states evolve at different rates, the mixture changes over distance. A neutrino born as one flavor can later be detected as another. This behavior is called neutrino oscillation. It proves that neutrinos have mass, although their masses are far smaller than those of other known matter particles. It also reveals that flavor is not fixed in the simple way an ordinary label suggests. A neutrino moves through space carrying several possibilities at once, and the balance among them shifts as the particle travels. Antineutrinos undergo a similar transformation. If the laws treat matter and antimatter perfectly, then neutrinos and antineutrinos should oscillate in corresponding ways after known environmental effects are included. But if their patterns differ, the neutrino sector may contain a new form of charge and parity violation. Experiments search for this by creating intense beams of neutrinos, sending them through long distances of rock and measuring which flavors arrive at large underground detectors. The procedure is then repeated with antineutrinos. Magnetic fields help select the charged particles that decay into one beam or the other. The neutrinos themselves pass through the ground almost unhindered, while a small fraction interact inside the distant detector and leave measurable flashes or tracks. The comparison is difficult because neutrinos interact so rarely, and antineutrino samples are often even harder to collect. Matter along the path can also affect neutrinos and antineutrinos differently, so the influence of the Earth must be separated from a fundamental asymmetry. Even so, long baseline experiments gradually narrow the possibilities. Hints suggest that the oscillations may not be exact mirrors, but the full pattern remains under investigation. A measured difference would satisfy only part of the cosmic requirement. It would show that neutrinos and antineutrinos behave differently, but it would not by itself prove that they create the matter excess. The connection depends on what neutrinos are at a deeper level. Most known particles are distinct from their antiparticles because they carry electric charge or another conserved property that reverses sign. A neutrino carries no electric charge. This allows a possibility proposed long ago: the neutrino may be its own antiparticle. Such a particle is called a Majorana particle. In that case, the distinction between neutrino and antineutrino would depend on the direction of spin and the way the particle participates in the weak interaction, rather than on a permanently separate identity. A neutrino could then behave as an antineutrino under the right conditions. Matter and antimatter would meet inside a single neutral particle. This possibility matters because it opens a route for changing lepton number, the accounting rule associated with electrons, neutrinos, and their relatives. If lepton number is not exact, an early process can create more leptons than antileptons. High-temperature reactions can then convert part of that lepton imbalance into a baryon imbalance. This broad mechanism is called leptogenesis. It does not begin by favoring protons directly. It begins in the hidden neutrino sector and allows the early universe to transfer the imbalance into the particles that later form atoms. Many versions introduce heavy neutrinos that no longer exist today. These hypothetical particles decay when the universe is extremely young. If their decays violate charge and parity symmetry, they produce slightly different numbers of leptons and antileptons. Because the universe expands and cools, the reverse reactions cannot fully restore the balance. The three Sakharov conditions appear in a new form. Particle numbers can change, matter and antimatter are treated differently, and the process occurs out of equilibrium. Standard model interactions active at high temperature then redistribute the asymmetry, turning part of the lepton excess into an excess of baryons. The heavy neutrinos disappear, but the imbalance remains. The mechanism is elegant because the tiny masses of ordinary neutrinos may point toward the existence of much heavier partners. In one common picture, the lightness of known neutrinos and the heaviness of unseen neutrinos are connected, like opposite ends of a scale. The heavier the hidden states become, the lighter the familiar neutrinos can be. The same physics that explains why neutrino masses are so small may therefore also explain why matter survives. Yet this elegance is not evidence by itself. Heavy neutrinos may lie far beyond the energy of any present accelerator. Their decays cannot be recreated directly, and several versions of leptogenesis can produce similar cosmic outcomes. Experiments must search for the surviving consequences. One crucial test is neutrinoless double beta decay. In ordinary double beta decay, two neutrons inside a nucleus transform into two protons, releasing two electrons and two antineutrinos. The antineutrinos carry away part of the energy. If the neutrino is its own antiparticle, however, an antineutrino emitted in one part of the process can be absorbed as a neutrino in another. The two invisible particles effectively cancel within the nucleus, leaving only the two electrons to emerge. The total energy of those electrons would then form a sharp signal, showing that nothing unseen has escaped. This decay would violate lepton number and demonstrate that neutrinos possess Majorana character. It would not automatically prove leptogenesis, but it would establish one of its most important ingredients. The difficulty is the expected rarity. A suitable nucleus may wait far longer than the age of the universe before undergoing the process. Experiments compensate by observing enormous numbers of nuclei in deep underground laboratories, shielded from cosmic rays. Crystals, liquid detectors, and other materials are watched for the exact energy pattern of two electrons appearing without neutrinos. Natural radioactivity, detector noise, and ordinary double beta decay create backgrounds that must be rejected with exceptional care. No confirmed signal has yet emerged. Each improved limit constrains the possible neutrino masses and the mechanisms that might connect them to cosmic matter. Oscillation experiments pursue another part of the answer. They compare how neutrino flavors change with how antineutrino flavors change. A stronger symmetry could support the idea that the lepton sector contains more charge and parity violation than the quark sector. But the link to the early universe remains indirect. The phase measured in oscillations may not be the same phase that governs the decay of hypothetical heavy neutrinos. The cosmos may use hidden parameters inaccessible to low-energy experiments. A future discovery could therefore strengthen leptogenesis without closing the case. The theory must still show that the measured properties produce the correct amount of matter under realistic early conditions. Neutrinos remain compelling because they occupy a boundary between the known and the unknown. They are established particles, not speculative additions. Yet their absolute masses remain uncertain. Their mass ordering is still being refined. Their possible Majorana nature is unresolved. Their pattern of charge and parity violation is not fully measured. Additional neutrino states may exist beyond the three familiar flavors. Each unanswered question intersects with the origin of matter. The quietest particles may carry the missing asymmetry because their neutrality allows transformations forbidden to charged particles. They may pass between matter and antimatter roles, create an imbalance among leptons, and hand that imbalance to baryons before the universe cools. Nothing in the evidence yet proves this sequence, but it connects several mysteries with unusual economy. The survival of matter, the smallness of neutrino mass, and the possibility that a particle is its own antiparticle may all belong to the same hidden structure. In underground chambers and distant detectors, researchers wait for rare interactions that could reveal that connection. A faint change of flavor, a difference between two beams, or two electrons emerging without missing energy, may point back toward the moment when the universe first chooses matter. The neutrino leaves almost no mark as it passes through the present world, yet in the first moments of time, its hidden identity may determine which world remains. The search for the origin of matter eventually reaches a boundary where the standard model can no longer provide a complete account. This theory describes known particles and three of the fundamental forces precisely. It predicts the behavior of electrons, quarks, photons, neutrinos, and the fields that govern their interactions. It explains the patterns seen in accelerators and the structure of ordinary matter. Yet when its known ingredients are placed inside the early universe, the surviving excess of matter remains too large. The theory allows some difference between matter and antimatter, but not enough. It permits baryon number-changing processes at high temperature, but not in a way that clearly produces the observed result under those conditions. It includes the Higgs field, but the transition associated with that field appears too smooth to drive the universe far enough from equilibrium. The failure is not dramatic. The Standard Model continues to describe every confirmed particle measurement with remarkable success. Its limitation appears instead as an absence, a missing mechanism between the first hot state and the matter-filled cosmos. That gap invites ideas that extend beyond the known laws without discarding them. One of the oldest possibilities is grand unification. In ordinary conditions, the electromagnetic, weak, and strong forces appear different in strength and behavior. At extremely high energies, however, their measured properties suggest that the differences may narrow. Grand unified theories propose that these forces are separate expressions of a single interaction that exists in the early universe. As the cosmos expands and cools, the unified force breaks into the distinct forces observed today. This deeper symmetry introduces new particles and new transformations. Quarks may change into leptons. Protons may eventually decay. Heavy particles may carry both baryon and lepton properties, allowing their decays to create matter and antimatter at slightly unequal rates. If these particles fall out of equilibrium as the universe cools, their disappearance can leave a permanent baryon excess. Grand unification provides all the broad ingredients needed for baryogenesis, but it places the decisive events at energies far beyond current accelerators. Its particles may be too massive to produce directly, and its clearest prediction, proton decay, has not been observed. Vast underground detectors watch enormous quantities of water or other material, waiting for a proton to transform into lighter particles. The silence does not eliminate every unified theory, but it removes simple versions and pushes the possible lifetime of the proton to immense values. The deeper force remains plausible, elegant, and unseen. Another path returns to the Higgs field. Today, the Higgs field fills space with a stable value that gives mass to many elementary particles through their interactions with it. In the hot early universe, that field does not necessarily occupy the same state. As temperature falls, it settles into the condition observed now. If this change occurs as a sharp first-order phase transition, bubbles of the new state can form and expand through the older phase. At their moving boundaries, particles interact under conditions that are neither uniform nor balanced. Reactions can distinguish matter from antimatter, and baryon number-changing processes can operate before the bubbles merge. The advancing walls can create a small excess and carry it into the stable phase, where it survives. This idea is known as electroweak baryogenesis. It places the origin of matter near energies that remain connected to particle experiments, making it attractive. Yet the known Higgs boson appears to make the Standard Model transition a smooth crossover rather than a violent bubble-forming event. Additional Higgs particles or other new fields may change that result. A richer Higgs sector could strengthen the transition and add new sources of charge and parity violation. Searchers at accelerators therefore look for extra scalar particles. Unusual Higgs decays and deviations in the Higgs boson's properties. So far, the observed particle continues to resemble the simplest Standard Model prediction. The door remains open, but no new field has stepped through it. Supersymmetry offers another extension. It proposes that every known particle has a heavier partner with a different type of spin. Fermions would have bosonic partners, and bosons would have fermionic partners. Such a structure can improve the way the fundamental forces approach unification and can introduce new sources of matter-antimatter asymmetry. Some supersymmetric particles could also provide dark matter, linking two major cosmic mysteries. Early versions seemed capable of supporting a stronger electroweak phase transition and richer charge and parity violation. Yet accelerator searches have not found the expected partners. The simplest forms are increasingly constrained, and the masses of any supersymmetric particles may lie beyond present reach. The idea survives in more complex forms, but its original promise has become harder to test. Other theories introduce new particles without requiring a full symmetry of this kind. Heavy bosons, sterile neutrinos, axion-like fields, or particles belonging to hidden sectors may decay in ways that favour matter. Some could exist only briefly during the earliest moments. Others may remain as dark matter today. Their interactions might be so weak that they pass through detectors unnoticed, leaving only gravitational effects or rare decay signatures. In these models, the visible universe may be only one part of a larger particle system. Matter survives because the hidden sector stores an opposite asymmetry, balances a conserved quantity, or changes the thermal history of the cosmos. The missing antimatter may not be missing in a simple spatial sense. Its accounting may be concealed in particles that do not form atoms or emit light. A more radical possibility places the mirror not in a distant galaxy, but across the beginning of time. Some cosmological models describe the Big Bang as a boundary between two expanding regions. On one side, time moves in the direction associated with the visible universe. On the other, a partner cosmos extends away from the same boundary with reverse charge, parity, and time orientation. From a larger mathematical view, the complete system can preserve a deep symmetry, even though each side separately appears matter-dominated. The other universe may be interpreted as the antimatter partner of this one, not because it occupies a location beyond ordinary space, but because it lies across the primordial boundary in the structure of space-time itself. Such proposals are speculative, and they do not yet rest on direct evidence. Their appeal lies in turning the imbalance into a matter of perspective. The full cosmos may remain symmetric while any observer inside one branch sees only matter. This approach can sometimes connect the nature of neutrinos, dark matter, and the initial conditions of the universe, but its predictions are difficult to isolate from other models. The partner universe cannot be observed as a neighbouring domain, and the early boundary remains hidden behind the hot beginning. The concept widens the meaning of antimatter without resolving the mystery by observation. Every proposed mechanism faces the same demand. It must create the correct excess, preserve it, agree with the measured properties of known particles, and avoid producing effects that experiments would already have seen. It must also fit the history of expansion, the abundance of light elements, the cosmic microwave background, and the formation of structure. Elegance is not enough. A beautiful theory can fail because it predicts proton decay too quickly, creates too much asymmetry, erases the excess later, or requires particles that should have appeared in accelerators. The early universe offers many possible pathways, but the present universe acts as a narrow filter. Most ideas do not pass through unchanged. The remaining possibilities occupy different scales. Electroweak baryogenesis may leave signatures in Higgs physics and future gravitational wave observations of an ancient phase transition. Leptogenesis may reveal itself through neutrino properties and lepton number violation. Grand unification may announce itself through proton decay. Hidden sectors may produce rare particles, dark matter signals, or deviations in precision measurements. A partner universe may remain almost entirely indirect, judged by the consistency and economy of the cosmological picture it creates. None has yet gathered enough evidence to become the accepted answer. The mystery, therefore, remains balance between success and absence. Physics understands antimatter well enough to create antiatoms, compare their spectra, and measure their fall under gravity. Cosmology understands the amount of surviving matter with great precision. The missing step lies between these achievements. Somewhere in the early universe, known symmetry must fail in a particular way, or a deeper symmetry must reveal itself across a structure larger than the visible cosmos. The answer may emerge from a rare decay in an underground detector, a difference in neutrino behavior, an unexpected Higgs interaction, a new particle in a collider, or a signal from an ancient cosmic transition. It may also require a change in how the beginning itself is understood. Until then, every atom remains evidence of an event without a confirmed mechanism. The universe exists, matter endures, and the laws that explain almost everything still do not fully explain why there is anything left for those laws to describe.